Okay, let's unpack this. Imagine for a moment a real cosmic head scratcher.
Right.
Finding stars that seemed, well, older than the universe they actually live in.
Right. This sounds impossible.
Exactly. But it was a genuine puzzle, not that long ago. Star ages were coming in around, say, 15 billion years,
Okay.
while the universe itself, people thought maybe 11 billion. Pretty mind-bending stuff.
Yeah, that's
Correct.
a fundamental conflict, isn't it? It suggests something's really wrong with either our cosmic measurements or our star models,
Hmm.
or both.
You got it. So for this deep dive, we're going to jump into that whole story, how scientists kind of tackled this age of the universe paradox.
Hmm.
And we'll look at how they figure out the ages of the oldest stars, especially focusing on one really fascinating one, nicknamed Methuselah, HD 1400283 technically.
Ah, yes, Methuselah, a famous case.
And we're using a document that really digs into the challenges and methods they used.
Right. So our mission here really is to understand how that first big paradox got sorted out, more or less. And also explore why we're still looking so closely at these really ancient stars, like Methuselah, trying to give you a clear picture of the cosmic timeline without, drowning you in jargon.
Perfect. Okay, so let's rewind a bit. That age paradox back then.
Right.
We said universe maybe 11 billion, some stars looking like 15 billion. How are they getting those star ages in the first place?
Well, it mostly came down to their brightness, their luminosity, and comparing that to theoretical models, how stars are supposed to burn fuel and change over time.
So brighter means younger, dimmer means older, roughly.
Generally, yes, for stars evolving off the main sequence, brighter, more massive stars burn through their fuel faster. Lower mass stars take much longer, dimming as they age in certain phases. The problem was some of these low mass stars seemed impossibly old based on the models in the assumed universe age.
Okay, but then 1997 happened, and something called the Hipparcos Catalogue.
Ah, Hipparcos, yes, a game changer.
Sounds maybe a bit dry, Hipparcos Catalogue, but you're saying it was crucial. How did better distance measurements suddenly fix this huge age problem?
It's amazing, isn't it? Hipparcos was a satellite that measured star positions and distances, specifically parallax, with much better precision than ever before.
Parallax, right? The apparent wobble as Earth orbits the sun.
Exactly. And this new data gave us better distances to crucial calibrators, like Cepheid variable stars. These pulsating stars are like standard candles,
Cosmic yardsticks.
pretty much.
Hmm.
Work by Feast and Catchpole using Hipparcos data showed Cepheids in a nearby galaxy, the Large Magellanic Cloud, were actually about a 9% further away than we thought.
Okay, 10% further. So what does that do?
Well, if they're further away but look just as bright from here, they must be intrinsically brighter stars. Right.
Ah, I see. Like seeing a headlight further down the road, it has to be a brighter light.
Precisely. And if the Cepheids are brighter, the whole cosmic distance scale built upon them needs adjusting. Everything gets pushed further out.
Including those old star clusters.
Huh.
Globular clusters.
Yes,
Mm-hmm.
those dense balls of old stars. They were also found to be more distant.
Okay.
And again, if they're further away, but we see them at a certain brightness, they too must be intrinsically more luminous than we thought.
Right.
Now, for stars in a cluster, their age is related to the luminosity of the stars just leaving the main sequence, the turnoff point. A brighter turnoff point means.
They're younger because they haven't dimmed as much yet.
Exactly. They were burning brighter, meaning they were younger than the previous dimmer estimate suggested. It showed how getting one rung of the distance ladder right affects everything else.
Wow. So just measuring distances more accurately basically made the oldest stars younger.
It did. It significantly brought those maximum stellar ages down, maybe to around 11 billion years or so.
And what about the universe's age estimate?
That got nudged up a bit too, maybe towards 12 billion years at the time. Suddenly the stars fit inside the age of the universe. The big conflict just evaporated.
That must have been a huge relief.
Oh, absolutely.
I mean, imagine grappling with that. Stars older than everything, it just doesn't work.
Right. And the source we looked at mentions astronomer Michael Feast being rushed off to a radio interview to explain it all. You can sense the excitement.
Yeah, like, stop the presses. The universe isn't broken after all.
Huh. Something like that.
Yeah.
It really shows science correcting itself, Better data leads to better understanding. Accurate distances were key.
Okay, so fast forward to now. You said that major age tension has mostly gone away. We're not seeing that huge 15 versus 11 billion year gap anymore.
Largely, no. Things are much more consistent.
So how are we measuring the universe's age these days? What are the main methods?
There are two main direct lines of evidence now. First, looking way back to the early universe.
The Big Bang's afterglow.
Exactly, the cosmic microwave background, or CMB. The Planck satellite gave us incredibly precise maps of it,
Okay.
and analyzing those patterns using our standard cosmological model, the lambda CDM model.
Lambda CDM. That's the one with regular matter, dark energy.
That's the one. Our best current recipe for the universe. Based on Planck data and that model, the age comes out as 13.787 billion years, plus or minus just 0.020 billion.
Wow, point zero to zero. That's incredibly precise. 20 million years margin of error on almost 14 billion.
It's pretty amazing, yeah. The precision is remarkable.
Okay, so that's method one from the early universe. What's the second?
Method 2 looks closer to home, in the local universe. It involves measuring distances to galaxies and how fast they're moving away from us.
The Hubble constant, the expansion rate?
Right, using things like Cepheids, again, the younger population I type,
Yeah.
and also sometimes older population 2 objects like those in globular clusters or certain types of supernovae.
And what age does that method give?
Interestingly, these local measurements often suggest a slightly faster expansion rate, which implies a slightly younger universe compared to the Planck CMB result.
Huh. So there's still a bit of tension there. Not as bad as before, but...
Exactly. It's a current area of intense research. Is the difference real? Is it some subtle error in one of the methods? Or does it point to new physics? It's often called the Hubble tension, but it's not a paradox like the old star age problem.
Okay, so maybe a bit of disagreement between the early universe and local universe measurements. But overall, that main age from Planck, the 13.787 billion years, does it generally line up with the oldest things we see inside the universe?
Yes, generally it does. It's considered consistent with the lower limits we get from other methods.
Like what?
Well, for instance, looking at the coolest white dwarf stars.
The remnants of dead stars.
Right, they're like cosmic embers cooling down.
Mhm.
The very coolest ones must have been cooling for a very, very long time, which sets a minimum age for the universe.
Okay.
And similarly, looking back at those globular clusters, the dimmest stars that are just now turning off the main sequence, the point where they stop burning hydrogen in their core. The fact that even the lowest mass, longest-lived stars are finally turning off tells us the cluster, and therefore the universe, must be at least that old. These different cosmic clocks all seem to tick roughly in sync with the CMB age.
That's reassuring. Multiple lines of evidence pointing roughly the same way.
Mostly.
Mostly. Which brings us back to Methuselah. HD 140283.
Indeed. Our cosmic outlier, potentially.
So while the big picture looks okay, this one star and maybe a few others are still problematic.
They're definitely interesting. HD 140283 is what we call an extremely metal-deficient subgiant. Meaning it has very, very low amounts of elements heavier than hydrogen and helium. Astronomers call these metals. And it's a subgiant. So it's already evolved off the main sequence, starting to expand. It's also moving very fast through our galactic neighborhood.
And why is it so interesting for figuring out age?
Because where it sits on the Hertzsprung-Russell diagram, that plot of star brightness versus temperature, its position is super sensitive to its age. Tiny uncertainties in measuring its properties, like its temperature or distance,
Can lead to big uncertainties in the age estimate.
Exactly. It's a tricky measurement, like
Yeah.
trying to read a clock with a very jittery second hand.
So what's the number? What's the latest age estimate for Methuselah?
Well, one of the widely cited recent estimates puts it at 13.7 billion years, plus or minus 0.7 billion years.
13.7 plus or minus 0.7. Okay, wait. The universe is 13.787 plus or minus 0.02. So Methuselah's best estimate is right there, but the uncertainty, it means it could be as old as 14.4 billion years.
Or as young as 13.0 billion, yes. But that upper end definitely bumps right up against or even potentially exceeds the universe's age, hence the nickname, after the famously long-lived biblical figure.
A cosmic senior citizen indeed. Now, our source mentions that getting reliable ages for lots of stars, like in big surveys, depends heavily on knowing their basic properties really well.
Absolutely. Temperature, surface gravity, metallicity, the metal content, and radius. You need those fundamentals accurately.
And they calibrate these against certain benchmark stars.
Correct. A set of well-studied stars where we think we know these properties very accurately. And HG 140283, Methuselah, is actually one of only 34 stars chosen as benchmarks for the Gaia mission.
Wow, so it's not just some random old star, it's meant to be a reference point.
Which makes getting its own age right even more important and perhaps more scrutinized.
Before we get deeper into its age measurements, the source made a point about accuracy versus precision. Can you remind us of that? It seems important here.
Yeah, crucial distinction. Precision is about how repeatable a measurement is. Do you get the same answer every time? Accuracy is about how close your answer is to the true value.
Like hitting the same spot on a dartboard over and over is precise.
Right, but if that spot isn't the bullseye, you're not accurate.
Got it.
So for Methuselah, the age estimate might be precise, like that next to 0.7 billion years. But there could still be underlying systematic errors in the models, in the measurements, meaning the estimate isn't perfectly accurate. The true age, the bullseye, might be slightly different.
Okay, that's a really useful thing to keep in mind. So this star, HD 14U283, people were interested in it for a long time because it was so metal poor, right?
That's right. Way back in the 1950s, astronomers like the Burbages recognized that stars with extremely low metal content must be very old.
Because they formed before lots of heavier elements were created and spread by later generations of stars.
Exactly. They're relics from the early universe, made mostly of the primordial hydrogen and helium from the Big Bang. So low metallicity is a strong indicator of great age.
And did early studies suggest it was super old?
Yes. By around the year 2000, some studies, particularly those considering that it might have enhanced amounts of certain elements called alpha elements.
Well, alpha elements like oxygen, magnesium.
Just like that, yes.
Right.
Those models were suggesting ages possibly over 14 billion years.
Which even back then was pushing the limits of the universe's estimated age.
Definitely raising eyebrows.
Okay. Then more recently, like 2013, there was a big study using the Hubble Space Telescope. What did they find?
Right. Bond and colleagues used Hubble's fine guidance sensors to get a much better parallax measurement from Methuselah, a more accurate distance, about 5 times more precise than the older Hipparcos value.
And a better distance means?
A better handle on its true luminosity, which feeds directly into the age calculation. They considered things like helium settling inside the star and an enhanced oxygen abundance.
Okay.
And their final number was 14.46 billion years, plus or minus about 0.31 billion, just accounting for those factors.
14.46 plus or minus 0.3. That's older than the Planck age of the universe, isn't it? Even considering the error bars.
It certainly is, yeah. They really put the tension back on the table for this specific star.
Was that the only study finding such an old age around that time?
No. Shortly after, in 2014, another group led by Vandenberg used very high-quality spectra detailed analysis of the star's light to pin down its surface chemistry. They came up with an age of 14.27 billion years, plus or minus 0.38. Again, very old, potentially conflicting with cosmology.
2 studies, better data, both pointing to an age possibly older than the universe. But the source we have says more recent estimates seem less in conflict. What happened? Did the models change?
It's likely a combination of factors. Stellar evolution models are constantly being refined. Maybe different assumptions about internal mixing, or updated nuclear reaction rates, or slightly different ways of treating the atmospheric properties. These can all suddenly shift the derived age. Our source mentions studies from 2018 and 2021 that seem to yield somewhat younger ages more comfortably within the universe's lifespan.
So it's still a moving target, it seems.
Very much so. These calculations are complex.
And the source also notes that as of when it was written, April 2022, there apparently wasn't an age published using the latest super precise distance data from Gaia's data release 2.
Right, which is slightly surprising, but these analyses take time. Gaia DR2 and subsequent releases like DR3 provide parallax measurements of unprecedented accuracy for millions of stars, including Methuselah.
So we expect that Gaia data should really nail down the distance part of the uncertainty.
It should significantly reduce the error bar associated with the distance, yes.
Yeah.
Which will then put more pressure on understanding the other uncertainties, the modeling, the composition, etc.
Okay, so summing up on Methuselah, where does the consensus lie right now? Is it a problem child or not?
I think most astronomers would say the overwhelming evidence points to the CMB-derived age of the universe, that 13.8 billion years, being correct. It comes from fundamental physics on a huge scale.
Right.
So if a single star like Methuselah appears older, the default assumption is probably that there's still some uncertainty or subtle error in the stellar measurement or the stellar evolution model for that specific unusual star.
We trust the cosmic measurement more than the individual star measurement, basically.
It's really, yes. But our source does raise that tantalizing possibility. What if, with even better data, a conflict remained? What if Methuselah, or another star, was definitively shown to be older?
What would that mean?
Well, it could mean our theories of stellar evolution are missing something crucial. especially for these very first-generation metal-poor stars. Maybe they burn their fuel differently than we think, or age in unexpected ways.
War.
Or, more dramatically, it could imply that our understanding of cosmology itself, the expansion history of the universe, maybe even the nature of dark energy or dark matter, needs revision. It would be a profound discovery.
Yeah, that makes you think. And the source suggests future Gaia data releases will be key to clarifying this.
Absolutely. Better parallaxes from Gaia should really sharpen the picture and help settle whether Methuselah is truly problematic or just sitting comfortably at the edge of old age.
Okay, so wrapping this up then. It seems that the big, glaring paradox from the late 90s stars older than the universe is largely resolved.
Yes, thanks mostly to improved distance measurements like Hipparcos recalibrating things.
But the quest isn't totally over. Pinning down the exact ages of the very oldest stars, like Methuselah, is still an active and pretty fascinating area of research.
Definitely. And it really highlights that difference between precision and accuracy we talked about.
Yeah.
Getting a very precise number isn't the same as knowing it's the right number, especially for something this fundamental.
Absolutely. Which leaves us with a final thought, maybe. What if? What if future data, really solid data, did show a star older than 13.8 billion years? What piece of our cosmic puzzle would we have to reshape?
It's a great question. Would it be stellar physics? Would it be cosmology? It reminds us that science is always probing, always testing, and sometimes you find things that make you rethink everything.
A humbling thought. Keeps things interesting, doesn't it?
Always.